Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So, welcome to the session on computational and statistical trade-offs. I guess I'd like to thank the IMS and MSR, of course, for all the support in putting together these sessions. I think it's great that we have this forum for a meeting of different communities that don't necessarily come into contact. And thanks also for all the speakers that have come and put their time. I think we have a nice lineup here for this session, too. So just to make a few comments. So this session has to do with problems that are kind of this interface between computation and statistics. We've very much seen flavors of this, for instance, in the previous talk, issues of what kind of trade-offs are there between the computational cost of procedures versus their statistical performance. And historically, this is something that's very much coming to the forefront because of big data. Traditionally, statisticians, at least the old-fashioned model was you have an estimator, you look at how it behaves, asymptotic normality, consistency, rates, but you don't really think about how to compute it. And many estimators, of course, are not really computable in poly time. Conversely, in optimization and algorithm design, people haven't always been thinking about statistical issues. Statistical problems bring very specific challenges to the table and sometimes enable you to use algorithms that maybe in a worst case setting aren't good, but in an average case setting that's appropriate for statistics can be very good. So just some broad themes. I think the speakers will touch on a subset of these. Lots of people are looking at analysis of computationally efficient procedures for statistical problems. The classical distinction in computational complexity, of course, is exponential versus polytime, but much more relevant in statistics and machine learning are hierarchies of polynomial algorithms, things like quadratic, linear, or even sublinear. If someone says I have a polynomial time algorithm, but it scales like n to the 10, and n is 1,000,000, it's essentially an exponential time algorithm for all practical purposes. And another thread that we'll see is people are often using algorithms as a form of regularization. So here, there's the idea that the algorithm choice itself is a design parameter. So things like early stopping, you run an iterative algorithm and you decide when to stop, that's a form of regularization. Dropout techniques in neural networks, that's again a form of regularization. Also things like bias variance trade-offs, these can also be explored by exploring the space of algorithms. So that's again a nice sort of interplay between algorithmic and statistical issues. Computational barriers, we've heard a fair bit about MCMC. MCMC realistically it's not really a controlled approximation unless you say something about mixing time. And it's pretty hard in general to say things about mixing times for a lot of these high-dimensional and quite complicated posteriors that come up in certain Bayesian models, but it's an interesting problem. There's lots of recent work these days actually showing there are gaps, that for some problems, if you have exponential time in computation, you can actually achieve a certain statistical error, and there's a gap. If you only have polynomial time, you can't match that exponential time bound. So there's gaps in things like planted clique problems and sparse PCA and certain forms of sparse regression. There's a very nice evolving literature in this area. I think the sort of holy grail here is the following question. Can we actually obtain principal trade-offs between the amount of computation that we can throw at a problem, where computation, in a general sense, it might be flops, it might be memory, it might be communication if we're in a distributed system. So can we get trade-offs between computational resources versus statistical performance? We'd sort of hope that as we throw more computation, we get better statistical results, but it'd be nice to be able to characterize the shapes of these kinds of curves. And there's, again, evolving lines of work on this problem. If we could answer that question, then I think we could really get very nice answers to problems in experimental design or sequential design, things that also known as active learning. Essentially, the question here is if there's a cost to collecting more data and there's a cost associated with performing computation, how should I trade off my resources? Is it better to collect more samples and use a cheaper algorithm, or is it better to collect fewer samples and spend more time with a more computationally intensive procedure? So these are some broad questions, and each of our speakers, I think, will hit on some subset of these questions. And so our first speaker will be Boaz Nadler. He'll be talking about edge detection on a budget.
First, I'd like to thank the organizers for a really great workshop. I'll talk about a particular problem within the instances that Martin highlighted. And this is joint work with Inbal Horev, who was a master's student who actually did the work, Ronen Basri and Meirav Galun at Weizmann, and Ery Arias-Castro at UCSD. This will have a slight overlap with the slide we've just heard from Martin. In many applications, we observe a lot of data, and me and Martin and many others have been trying to think what are interesting statistical problems related to that. So one is that you have so much data, it does not fit or cannot be processed on a single machine. And a very common approach nowadays is distributed learning. And then you can ask yourself, how much accuracy did I lose by splitting the data over many machines? And many people have done work on this. I'm pointing out to a very recent work of myself. However, this will not be the focus of my talk. The focus of my talk will be a different problem related to a lot of data. And that has to do with maybe you have so much data that if you apply a standard algorithm, it will be too slow or take too much computing power. And then you can think about two key challenges. One, let's call it a bit more practical. There's obviously a need, and we've heard that in many of the previous talks, to develop extremely fast statistical inference algorithms. And ideally, you would like them to have linear or maybe even sublinear complexity. And more on the theoretical side, we certainly would like to understand fundamentally what are lower bounds on what statistical accuracy we can achieve when we have computational constraints. And this is exactly what I want to show you today for a very specific problem, a problem that came from my collaborators in image processing and computer vision, has to do with detection of edges in large and very noisy images. So we were lucky. So these are general challenges, and we don't have answers to them. For this specific problem, the way we formulated it, at least, it had a sufficiently simple geometric structure that we could actually give precise answers to these questions. So what is edge detection? You take an image. There is an image, n1 by n2 pixels. It's just a matrix of values. And your goal is to detect edges in this image. It's typically boundaries between objects. And essentially, you can think about it as there are curves in this image, so that if you take the gradient of the intensities along in the normal direction to the curve, you get large gradients. Okay? It's a fundamental task in low-level image processing. It's a well-studied problem. There are tens or even more of different algorithms and a well-understood theory. Our interest was detecting edges in noisy and large 2D images or even 3D video. You can think about tracking. And motivation for large is clear. We just have larger and larger or better and better high-resolution cameras. So you can easily get images of size 1,000 by 1,000 pixels. But actually, there are also surveys, especially satellite ones, where you have images of sizes of 40,000 by 40,000 pixels and more. Motivation for noise. So again, in some applications, you have images in non-ideal conditions, like poor lighting or fog. Various surveillance applications. You can also think about real-time object tracking in 3D video, where you have very short exposures and very noisy frames. I am going to have one image prior, and that is that I'm going to be interested in long and straight edges. We'll see that image. So here is just an illustrative example. This is actually an image we took out from the web. It's quite large. It's roughly 2,000 by 2,500 pixels. So for example, one of the most common helicopter accidents is that they crash into power lines. Okay. So everybody can see this power line and this transmission power and these power lines. Can you see there's another one here? So if there's another one here, can you? I mean, there are very faint lines here as well. Okay. All right. So if you open Wikipedia edge detection, you'll see that the most common algorithm to detect edges is by John Canny. It's called the Canny edge detector. What it does, it takes this image, goes pixel by pixel. At each pixel, computes, convolves it with a Gaussian to attenuate the noise a little bit, and then looks if there are high gradients. If there is, it says at this pixel there is an edge. So it's a very fast algorithm, complexity linear in the number of pixels, but it's local in nature. So it does not really work well at low signal to noise ratios. And if you apply it to the image I showed you before, it easily finds all of these power lines, but of course it finds the bushes. It does not find anything in the second transmission line. So at the other extreme, there are more sophisticated methods that are global in nature. And we also have some theory for which edge strength we can detect. This is also where practice and theory depart, because these methods are theoretically efficient. They're multi-scale. They run in n log n time. It's just that there's a constant there that is quite high. So they're practically slow. So I took the algorithm developed by some of my collaborators with Achi Brandt, who's an expert on multigrid. And yeah, in practice, it runs roughly like minutes on single images and hours on video. It works well. It's just very slow. You need to better control the false alarm, but it easily detects these power lines. It just takes minutes on a single frame. So the challenge, or this is a toy problem, but the challenge in similar problems is you want to devise, on the one hand, algorithms will be extremely fast, but on the other hand, you want them to be robust to noise. And what I want to show you is an approach to do so which is sublinear. In other words, I want to detect long edges. So think about the following setup. You have hardware, it takes images, it may take many images. You want to detect if there are long edges in them, but just transferring the data from the memory to your computer is extremely slow. That's one of the bottlenecks. You want to detect if there is structure without even touching all of the data. In other words, in sublinear time. And specifically in complexity, which goes like n to the alpha, with the alpha which is strictly smaller than 2. And once you formulate this type of problem, many questions arise. So one is statistical. What did you lose? You're not going to touch all of the data, so obviously you will lose something, and the question is exactly how much. What's the trade-off? There's also a computational question related to experimental design. Which pixels should I observe? And on the very practical side, we want to design an algorithm which will have sublinear time and hopefully even match the lower bounds we'll get from the statistical theory. So I'll skip this. So here we need to formulate some model. For the theoretical part, I'm going to assume a very idealized model. I'll later on show you that our algorithm works reasonably well on actual images. But our model to do the analysis is that what I observe is a noise-free image I0, corrupted by noise, additive, Actually, in the analysis, we even assume it's Gaussian. And my goal is to detect the edges in the clean image I0 from the noisy observed I. And my assumptions are that my clear image contains only few step edges. A step edge is just that the intensity is one constant on one side of the edge and a different constant on the other side of the edge. So there's a sparsity assumption in there. A second assumption is that the edges that I'm interested in are straight and long. And it makes sense. If I cannot detect in sublinear time an edge who's only 5 pixels in length. And the definition of what is a signal-to-noise ratio of an edge is just the jump, the edge contrast, divided by the noise level sigma. Okay. And so these are the questions. Which pixels should I sample? What are fundamental lower bounds? And what's the trade-off between statistical accuracy and computational constraints? So I'm going to do that. The analysis I'm going to do on a very simplified class of images, and I'm going to do a worst-case scenario. So the class of images I'm going to analyze is the following class. I'm going to assume that my observed image I either contains only noise, or it may contain a single long fiber that goes from one side to the other plus noise. I don't know neither its orientation nor its location. And I'll focus on a worst case scenario. And here's the first lemma that is very easy to prove. It says that if you observe n to the alpha pixels, and alpha is smaller than 1, then provably there is an edge that you will not be able to detect, no matter how strong it is. It's very easy to prove. If you observed less than n pixels, take a single column. There is at least one row that you haven't observed any pixels in it. I'm going to pass my edge exactly through that row. So you don't know that it's there. Okay? Here's a less trivial result. It says that, okay, another thing I didn't mention, I'm thinking here about non-adaptive sampling, meaning that I decide which pixels to sample in advance. Okay? It's not as if you can also, a different interesting problem is an adaptive sampling where you observe a pixel, based on the result, you can decide where to observe a pixel next. I'm not doing that. I set up in advance which pixels I want to observe. So if I have a budget of S pixels, and let's assume for simplicity that S over N is an integer, then we have a notion of what is an optimal sampling scheme. I don't have time to go into the exact details, but an optimal sampling scheme is the one in which, in a worst case scenario, it has highest detectability power. So any optimal sampling scheme must distribute its budget evenly. It must observe exactly S over N pixels per row. And in particular, if you decide just to sample whole columns, this is an optimal sampling scheme for the class of images I had before. Okay? And this is very attractive because this is going to the practical side. Fetching from memory contiguous columns is fast. Okay?
I was going to ask, it seems asymmetric in columns versus rows.
So I was very careful to assume that my pixels go from left to right. What we do in practice is we search for edges on the original image I, and then we transpose it and reapply our algorithm. Okay? Okay. I mean, we could have also had a version where we sample whole rows. Okay. Regarding the trade-off between statistical accuracy and computational budget, remember that's the definition of edge signal-to-noise strength. We could then prove the following theorem that if you have budget, there's another issue I didn't say. I write here complexity, but actually, for our implementation, complexity and budget are nearly the same because we have an algorithm. I don't think I'll have time to describe that. If you give me S pixels, its running time is roughly S. It's S times a logarithmic factor. So runtime complexity and budget are the same. So let's say at a budget of n to the alpha pixels, up to constants, the edge strength that you can detect roughly scale as follows. So here is alpha. So remember, if alpha is less than 1 in a worst case, there are strong edges that you cannot detect. If alpha equals 2, you've seen the whole image. You can do whatever you want. And alpha equals 1 means that you can see maybe 1 or 2 or 3 columns. And any edge which is below this curve, you cannot detect, asymptotically at least when n is very large. And any edge whose strength is above this curve is easily detected. If you go to our paper, we show empirically that our detection algorithm exactly traces. Oh, yeah.
What does the detection algorithm do for empirically for alpha less than 1? Does it sort of confuse?
No. So you can talk about either worst case detectability or average detectability. So now to discuss average detectability, you need to have a prior, not a prior, or a sampling distribution where edges come from.
Yeah, or you could rotate the image randomly.
Yeah, but this is a worst case scenario, if you wish. I should say that given that for alpha between 1 and 2 we sample whole columns, actually our detection power for edges is the same regardless of their location and orientation. So okay. So here is so that was the theoretical part. I'm shifting gears to the
Sorry, just one question. So is it in a minimax sense? Or
this is for this specific problem. This is a minimax result under constraints.
Signals you allow. Is it that you allow signals which go from left to right, but you don't? But you know that the full extension goes from left to right, and the width
can be even 1 pixel wide.
Or is it known? Or?
No, it's unknown and can be as small as 1 pixel.
Okay.
In the power lines I showed you, they are really like the power lines I showed, the image with the power lines, the width is 2 or 3 pixels wide.
Why do you then get a log factor in your lower bound?
Because it's a multiple hypothesis testing problem. I have many different orientations.
Sorry. So then I didn't understand. So I thought you know that it goes. Oh, okay. Because you still go from left to right, you get a log factor. So, okay, I understand.
Yeah.
Okay.
Yeah. That's the class on which I analyze. It's all images that are either just pure noise, there's no edge, or there is there is a fiber actually. It goes from left to right. I just don't know neither the starting point nor the.
Thanks. I get it.
Okay. So I've covered a little bit of the theory. Let me shift gears and describe in 2-3 words the algorithm. So what we actually do, and it also relates to Axel's question, in practice, edges not necessarily go from left to right. So what we do in practice is we sample several strips, okay? Because an edge may only go from here to here, okay? In each strip, we look if there are edges in it or not. Let's assume that here I detected there is an edge, here I detected that there is an edge. Then I also fetch the pixel values only in this region, okay? So for those who are knowledgeable, there's something in statistics called group testing. This is somewhat analogous to group testing. I'm looking at the pixels here, looking at the pixels here. If I don't have any evidence for an edge here or for an edge going through here, I'm not going to look at the pixels in between, okay? So that's why there is a simple geometric structure that allows me to have a sublinear time algorithm. Now, there are many other things that you need to do. For example, you need to validate if there is an edge. You need to localize it if it doesn't go from left to right, only somewhere in between. Let me show you some results. So here is just a simulated image. You see various rectangles. Signal to noise ratio is 1. It's not very low. our visual system can easily see everything here. This is the result of Canny. This is our algorithm. We don't detect these because they're just too short for our method. Here is a comparison of our algorithm's runtime with a supposedly efficient multi-scale algorithm to detect straight edges. This is a image width n. So this is n log n or something. Ours is it's sublinear, so it increases, but you hardly see it on such a scale. And here is the result of our algorithm on the image I showed you before. Okay, and this is roughly looking at something like maybe 10% of all image pixels. So we sampled, I don't know, maybe 8 strips or something. By the way, one moment. This is just an image we took from the internet. It's fog, it's not Gaussian noise. We estimate the noise level only from the strips in which we sampled. No tuning parameters to the algorithm other than that. Question? Yeah. No. We sample this strip, this strip, this strip. We equispaced strips. Okay. Yeah, you could think about a checkerboard design. It would not be friendly to the architecture on the one hand. It would not be friendly computationally on the other. Here are another few images, a forest with a road. So these are images with texture. We can still do something reasonable. A soccer field. And I'd like to summarize. What I've shown you is on a very specific problem that for that one we could actually study in detail the statistical versus the computational trade-off. I think we developed possibly the first sublinear edge detection algorithm. We're not aware of other people who have done it. There are many open challenges and questions. Specifically for edge detection, this is basically a proof of concept. You really need to be able to deal with slightly curved lines, with variable contrast, with texture, etc. A real challenge is how to do this in 3D, because a 3D video is immediately hundreds of gigabytes, or several gigabytes can easily be. And I think in more general, understanding this trade-off between statistics and computational constraints for other problems, whether in image, astrophysics, or other big data problems in general, I think it's a fundamental and interesting problem. So research is a very long path. Come and join us. The road to infinity. Thank you. Yeah.
Go ahead. It seems, I may be wrong, but it seems that doing this in the sublinear time depends on only using long edges. So if you look at short edges,
I completely agree.
So then
you have an object and you want to define something very small. You cannot do it in sublinear time.
So then doing the small edges is a much more difficult problem.
I think you can provably show that you cannot do it in sublinear time.
Okay, all right.
Think about an image where there is no edge. It's just you're looking for a spike, like a star in astrophysical. You're looking for a very small region with high intensity. How can you do that if you don't observe all of your image? Excuse me?
We can use the same ideas, but now do this in parallel by splitting the image into different.
Parallel still is not sublinear. Parallel is our algorithm easily parallelizes. You can so on a GPU architecture, you can each strip send to a different GPU and then gather the results. Yeah, sorry.
Go ahead.
So it's interesting when you mentioned going to 2D curves. If you still assume the curves are long, I'm just curious if you would guess that the time being sublinear, it would depend on the average curvature or second derivative of the curve.
You're going to have to assume a bounded curvature, otherwise it will not work.
Do you think there's a critical curvature then where you go from sublinear to linear? That would be.
That's a good question. We're working on it right now, and I haven't thought about it yet. Yeah. Yeah.
It must also depend on things like the thickness of the lines relative to the density of the pixels. I mean, you don't need. So, does it? I mean, I'm thinking that maybe some of the work could ultimately have impact on the design of the instrument used to measure an image. If you want to find a line of a, because there's no point in measuring pixels at too high resolution to detect the lines you're interested in.
Okay. So I'll say as follows. If you're looking for objects which have a minimal width, you can, so to speak, subsample.
Yeah.
But if you want to detect edges which can be 1 or 2 pixels wide, then you cannot subsample. So.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.